Hello, I'm Joseph Kasser, and welcome to this podcast where the AI team does a deep dive into some application of systems thinking.
Have you ever perfectly executed a massive, complex project, like hitting every single deadline, staying meticulously under budget?
Which is rare enough as it is, right?
Right, exactly. But then you do all that only to realize at the very end that it doesn't actually solve the problem you set out to fix.
Oh, that is the worst feeling.
It really is. Like, you build this highly optimized, ultra-low latency data pipeline, but then it turns out it was pulling from completely the wrong database.
Yeah, you essentially engineer the perfect solution to, well, completely wrong problem.
Exactly. And today, we're going to explore how massive institutions try to avoid that exact nightmare scenario. We are going on a mission today, literally.
I like that.
Thanks. The mission of this deep dive is to unpack two dense but honestly incredibly fascinating sources. First, we have this historical breakdown of systems engineering tracing all the way back to its origins in the 1950s. And second, we've got the October 2023 Department of Defense Mission Engineering Guide version 2.0.
And, the evolution between these two documents, it really tells a story about how our philosophy of solving complex problems has, well, shifted over time.
Right.
How it derailed
Yeah.
and how it is now sort of attempting to course correct using modern technology.
So to get through all this, we're structuring this deep dive as a Q&A. I'll be guiding us through the source material, firing specific questions at you to answer one overarching massive question that ties these two documents together.
Bring it on.
I am looking for a definitive yes or no by the end of this conversation.
Okay, the pressure is on.
Here is the question. Is the modern military concept of mission engineering actually just a return to the original analytical engineering paradigm of systems engineering that kind of got lost decades ago?
Wow.
Yep.
Okay, yeah, it's a question that really forces us to look closely at how the engineering discipline kind of lost its theoretical soul, I guess, and how modern computation is trying to buy it back.
Okay, let's unpack this. Let's start with the historical roots of systems engineering, or SE, based on the historical text we have. If SE is the process of, say, building out a massive global data center network, what parts of that construction process are we historically talking about?
Well, from the 1950s through the 1970s, systems engineering practice actually involved three distinct streams of work.
Okay, three streams.
Yeah. The first stream is management. And in your data center analogy, this isn't like racking the servers or writing the routing protocol.
Right, it's not the hands-on stuff.
Exactly. This is securing the zoning permits, coordinating the hardware vendors, creating the deployment schedule, and managing the risk register. It's the governance of the entire process.
So the paperwork, the milestone tracking, and the project managers.
You got it. Then the second stream is what the text calls analytical doing.
Analytical doing.
Yeah, which is kind of a clunky phrase.
Yeah.
But it's the intellectual act of creating the solution. It's the synthesis, the modeling, the boundary analysis.
Okay, so sticking with the data center.
Right, so that would involve understanding how, say, the cooling systems interact with the server heat output. So you don't accidentally, melt down a rack during peak traffic.
Ah, okay.
It's heavily focused on what the system must be and the behavior that sort of emerges from its individual parts interacting.
Got it. And the third stream?
And finally, the third stream is empirical testing.
Which would be, I guess, actually firing up the servers, pushing a simulated load, and making sure the latency numbers match what the analytical model predicted.
Precisely. Verification against the actual operational environment. And those three streams, management, analytical doing, and empirical testing, they're supposed to be present and balanced on every major program.
But based on the historical text, they did not stay balanced, right?
No, they didn't.
One of those streams completely overpowered the other two.
Yeah, and what's fascinating here is how pioneers like Good, Hall, and Domash, they originally defined systems engineering as being inherently about those component interactions and whole system optimization.
Right.
Back in 1962, Domash and Laudeman were teaching Air Force engineers that SE was an approach where, and I'm paraphrasing a bit here, each component is designed to fit properly with the other components rather than to just function by itself.
So they were looking at the big picture.
Exactly. They wanted to deeply understand what the system must be through that analytical doing stream. But a profound structural flaw kind of haunted the discipline from the start.
Okay, let's define that flaw. Why couldn't they just, stick to the original vision of whole system optimization? What happened?
Well, the management stream, captured the institutional definition of the discipline way before the analytical doing and testing streams could establish a really firm scientific and mathematical foundation.
Oh, I see.
I mean, think about the computational tools available in the 1960s and 70s. Managing schedules, drawing up Gantt charts, and tracking budgets, that's all relatively straightforward to standardize across a massive institution.
You just need paper and a pencil, really.
Right. But mathematically modeling the nonlinear interactions of thousands of complex components in a dynamic, unpredictable environment.
Yeah, that's a whole different beast.
You simply cannot run a stochastic model of 1,000 interacting variables on a slide rule or, an early mainframe with just kilobytes of memory. The theoretical and computational foundation for the analytical stream just wasn't mature yet.
So because they lacked that analytical foundation, they compensated with process.
Exactly.
The discipline became famous for milestone management and configuration control rather than the intellectual act of actually architecting the solution.
Yeah, it became very bureaucratic.
And this matters to you, the listener, because anytime you find yourself bogged down in project management red tape, like filling out endless status reports instead of actively problem-solving the architecture of your project, you are experiencing this exact historical bifurcation.
Oh, 100%.
You are trapped in the management stream.
Systems engineering basically became synonymous with building things right, according to the schedule and the requirements document, rather than continuously analyzing if they were building the right thing.
Okay, so what does this all mean for the modern military? That brings us to the October 2023 DoD Mission Engineering Guide.
Yes, the big pivot.
What exactly is mission engineering, or ME, and how does it address this historical drift?
Well, the 2023 guide defines mission engineering as an interdisciplinary process that decomposes missions into their constituent parts to explore and assess relationships and impacts in executing the end-to-end mission.
Okay, that's a lot of jargon. Let's break that down into practical terms.
Fair enough. The guide makes a direct contrast that I think clarifies the entire philosophy. It explicitly states that the systems engineering process aids the department in building things right.
Okay, SE is building things right.
Right. But the primary goal of mission engineering is to identify the right things to build in the first place, to achieve the intended mission outcomes.
Building things right versus identifying the right things to build. That is the core distinction.
It is.
But let's play devil's advocate here for a second. It is super easy to write a manual saying, hey, we are going to figure out the right things to build.
Oh, sure. Words are cheap.
Right. But if you spend years building these massive digital sandboxes and running endless simulations to figure out the quote-unquote right thing, don't you risk severe analysis paralysis?
That is a huge risk, yeah.
Like, how does ME prevent us from endlessly modeling in a digital twin while our adversaries are actually out there bending metal and building hardware?
Well, the defense against analysis paralysis is extreme methodological rigor and early computational disqualification.
Early disqualification.
Right. The ME methodology walks through several strict sequential phases that are explicitly designed to kill bad ideas quickly before any metal is ever bent.
Okay, walk me through the phases.
Step 1 is defining the problem or purpose. Like, are we trying to identify a capability gap? Are we trading potential solutions? Once you know the purpose, you move to step 2, which is mission characterization.
And what does that entail?
This is where you develop the operational context using scenarios, epochs, and vignettes.
Okay, the text mentions an example of a year 2040 base defense scenario focused on the Western Islands region. What actually goes into defining an epoch and a vignette?
Well, you aren't evaluating a new radar system in a vacuum. You place it in a specific future time frame that's the epoch within a highly detailed operational context, which is the vignette.
So it's heavily contextualized.
Extremely. You define the physical environment, incorporating historical weather patterns, sea states, and even electromagnetic interference.
Wow, even the weather.
Oh yeah. You define the specific threat vectors from adversaries and the allied forces that would realistically be available in that theater at that exact time.
Okay, so you construct the boundaries of the sandbox before you even evaluate the tools.
Exactly. And once those constraints are built, you move to step 3, which is where ME connects abstract goals to measurable data. This is defining metrics.
Ah, the metrics.
Yes. The DoD guide introduces a strict hierarchy of measures, MOPs, MOEs, and MOSs.
Let's unpack that hierarchy. Give me the breakdown of those acronyms.
Sure. So MOP stands for Measure of Performance. These are the measurable physical characteristics of a specific system.
Like what?
Like what is the processing speed of a server? What is the radar's maximum detection range? It's the raw stats. Moving one level up, you have MOE, measure of effectiveness.
Okay.
This measures the operational effects that come from executing tasks within the mission context.
Okay.
For example, how many enemy targets were successfully tracked simultaneously.
So it's applying the performance to a task.
Right. And finally, at the very top, you have MOS, measure of success. This evaluates the overarching mission objective.
The big picture.
Exactly. Did the joint force successfully defend the Western Islands base from a coordinated attack in less than 5 days?
Okay, let's map MOP, MOE, and MOS to a complex tech sector problem, just so it translates outside of a purely military context for the listener.
I think that's a great idea.
Let's say your company's overarching mission is to successfully launch a new software application and retain users.
Okay.
Your MOP measure of performance might be your server's compile speed or the database latency. It's purely technical.
Right.
Your MOE measure of effectiveness is, say, the user's successful login rate, or the load time of the user interface during peak traffic.
Exactly, the operational effect.
And then your MOS measure of success is whether you hit a 15% increase in Q3 recurring revenue because users actually stayed on the platform.
That's a perfect analogy.
Mm-hmm.
And what mission engineering does is ensure that an institution doesn't obsess over the MOP, like having the fastest server compile speed, if it doesn't actually contribute to your MOS, which is retaining users and driving revenue.
Because you could have the fastest server in the world, but if the app is useless, who cares?
Exactly. If your objective is user retention, but your systems engineers are spending millions optimizing database latency while completely ignoring a fundamentally broken user interface, you are building the wrong thing.
Yeah, SE might perfectly engineer the database according to the requirements document, but ME steps back and evaluates the entire architecture against the final measure of success.
Right. And to evaluate that architecture, you have to map out all the interacting elements.
Which sounds incredibly complicated. I mean, in a military context, we are talking about satellites, surface ships, bomber aircraft, and ground troops, all trying to execute a unified objective.
It is massively complex.
How do they orchestrate that level of complexity?
Well, if we connect this to the bigger picture, the guide introduces the concept of mission architectures, which consist of two vital elements. The foundational element is the mission thread.
The mission thread.
Yeah. A mission thread characterizes the generic sequence of events, tasks, and activities required to achieve a mission. It focuses entirely on what is being done, independent of who or what is actually doing it.
So it maps out the verbs.
Exactly. The text highlights a kinetic kill chain mission thread known as find, fix, track, target, engage, assess, or F2T2EA.
F2T2TA, okay.
That is the sequence of necessary tasks, the verbs. The second element is the mission engineering thread, or MET.
MET, got it.
This is where you transition from generic tasks to specific material solutions. You assign actual actors, systems, and technologies to those verbs.
So you turn the generic engage task into a specific quantifiable action.
Right.
Instead of just saying strike the target, the MET specifies employ a GPS-guided standoff missile launched from a B-52 bomber aircraft.
Exactly. You assign the nouns to the verbs. And when you interconnect all these diverse mission engineering threads within a specific scenario, like linking the satellite, finding the target to the bomber, and gating it, you create what the guide calls a kill web.
A kill web.
Yeah, an inclusive dynamic set of multiple integrated threads.
Okay, so we have our MIT-Ts mapped out. We know we are using a bomber with a GPS missile in a 2040 scenario. But how do we rigorously test this without actually fighting a physical war? The outline points to an analytical engine and a framework called run matrices.
Yes. The run matrix is essentially the core computational engine of mission engineering analysis. It provides a highly structured evaluation framework.
How does it work?
You begin with a baseline approach. So our baseline METIS of the bomber-launched GPS missile. Then you develop alternative approaches to see if a different configuration yields a higher measure of success.
Oh, I see.
The text provides a specific excursion for this. What if we substitute the launch platform? What if we employ that exact same GPS-guided glide vehicle, but we launch it at an extended range from a surface ship instead of a bomber aircraft?
Okay, and here's where it gets really interesting. You aren't just sitting around a conference table debating the merits of a ship versus a bomber based on, like...
gut feeling or institutional bias.
No, absolutely not.
You have to prove it mathematically.
You do. The analytical methods mentioned in this guide for evaluating these run matrices are incredibly heavy. We're talking Monte Carlo simulations, Bayesian analysis, Markov chains, stochastic modeling.
It is heavy math.
Let's break down the mechanics of this math. Why do you need Monte Carlo simulations and stochastic modeling just to test a missile launch?
Because warfare, much like any complex global market, is inherently probabilistic, not deterministic.
Probabilistic, meaning it's not a guaranteed outcome.
Exactly. You cannot just run a simulation a single time and declare that the surface ship is the definitively superior choice.
Because things change.
Right. Weather patterns shift dynamically. Radars experience random anomalies. Adversaries adapt their tactics unpredictably. Stochastic modeling introduces the random noise of reality into the digital environment.
Okay.
And then Monte Carlo simulations take that stochastic model and run the scenario thousands or even millions of times.
Wait, really? Millions of times?
Yes. Because by injecting random variables based on real-world probabilities across millions of iterations, you generate a statistical distribution of potential outcomes, rather than just relying on a single, brittle prediction.
So it gives you a statistical confidence interval.
Precisely.
Like, out of 1 million simulated engagements, the surface ship achieved the measure of success 82% of the time, while the bomber only achieved it 64% of the time, given all those randomized variables.
Yes, that is exactly how it works.
That's wild. Okay, what about Bayesian analysis and Markov chains? How do those function within the run matrix?
Well, Bayesian analysis is about updating the probability of an outcome as new evidence is introduced during the simulation itself.
Oh, so it adapts on the fly.
Right. You don't just have a static, unchanging probability of a radar detecting a threat. As the simulation progresses, say, as the threat moves closer or simulated weather clears up, the model updates the probability of detection dynamically based on that new data.
That makes total sense. And Markov chains?
Markov chains model state transitions, where the probability of moving to the next state depends only on the current state.
So if a target transitions from the state of tracked to targeted, the model calculates that probability based entirely on the conditions in the tracked state.
Without needing the entire historical memory of how the target was originally found in the first place. Yes.
Okay, got it.
And all these mathematical methods, they're woven together using digital engineering software languages like SysML or systems modeling language.
Which is ML.
SysML allows engineers to create relational, computational representations of these mission threads. It isn't just a static document or a spreadsheet.
Right.
If an engineer changes the payload weight of the missile in the SysML model, the software automatically recalculates the thrust requirements.
Which changes the required fuel load?
Exactly. Which instantly alerts the bomber modeling team that the weapon's physical dimensions have changed and it will no longer fit in the payload bay.
Wow. You are building massive, dynamic digital twins of the entire operational environment.
It's incredible, really.
You quantify the emergent behavior of the whole system interacting, searching for the accuracy, precision, and statistical confidence of the results.
Yep.
So if the SysML models and the millions of Monte Carlo iterations prove that the surface ship increases your measure of success, then the surface ship is the right thing to build.
The math makes the decision. The pieces are all on the board now. We've established the history and the modern computational framework.
Right. So I'm going to ask the core question of this deep dive. I need a definitive yes or no.
Okay, let's hear it.
Based on these sources, the history and the mathematics we just explored, is mission engineering actually a return to the original analytical engineering paradigm of systems engineering?
Yes. Definitively, yes.
Okay, justify that answer. Walk me through the comparison.
Well, if we compare the two paradigms side by side, the lineage is undeniable. The management paradigm of systems engineering that dominated for decades was focused heavily on institutional governance.
The risk registers, the schedule milestones.
Right, and ensuring the final product met the predefined requirements document. It was entirely about building the system right. But recall the original analytical paradigm from the 1960s.
Right, Dimash and Laudeman.
Yeah. They explicitly stated in 1962 that systems engineering is an approach where each component is designed to fit properly with the other components rather than to function by itself. They wanted whole system optimization.
They desperately wanted to understand what the system must be.
Exactly.
They just didn't have the computational tools to do it back then. They couldn't test those component interactions at scale because SysML and distributed cloud computing, didn't exist.
And that is the crux of it. The 2023 Mission Engineering Guide represents the practical realization of that 1962 vision. Mission engineering does exactly what those early pioneers wanted, but it finally possesses the scientific and digital foundation that the original analytical stream fundamentally lacked.
It's all coming full circle.
Through digital engineering, relational SysML models, and computational run matrices, utilizing Bayesian and stochastic mathematics, ME evaluates the emergent behavior of the whole system interacting in a mission context.
It evaluates the entire kill web.
Yes. It shifts the discipline's focus back from simply managing the process to the rigorous intellectual act of architecting the solution.
It completely reclaims the analytical doing stream.
It really does. And, this raises an important question for anyone managing complex projects today, whether you are engineering national defense architectures, writing enterprise software, or building physical infrastructure.
What's the question?
Are you just managing your baseline, like tracking milestones on a static spreadsheet, or are you actively modeling the alternatives and variables to ensure you're actually solving the right problem?
Because if you're only managing the baseline...
You are operating with a 1970s methodology.
Oof. That is an incredible framework to apply to our own work. So, to wrap this up for you listening, whether you are designing multi-domain defense strategies to deter global conflict in the year 2040, or you are just planning a corporate infrastructure overhaul for next quarter, you have to marry the analytical doing with the management.
Absolutely.
You have to deploy the analytical rigor to figure out the right thing to build before you ever start worrying about building it right. Because if your ultimate measure of success is failing, perfectly executing your granular measures of performance will not save your project.
Well said. And that leads to a final, somewhat provocative thought to leave you with, building on everything we've just discussed about digital modeling and massive computational data sets.
Lay it on me.
So mission engineering relies heavily on simulating these run matrices with red forces representing the adversary and blue forces representing allies. We talked about Monte Carlo simulations running millions of times to find statistical confidence.
Right, the immense computational heavy lifting.
Well, consider what happens when we inject generative AI and machine learning directly into the heart of this analytical engine.
Oh, wow.
We are rapidly moving toward a reality where AI doesn't just execute the simulation of a human-designed run matrix, but it actively designs the alternative mission engineering threads itself.
It builds the alternatives.
Exactly. Will future mission architectures be built, tested, and effectively fought in billions of simulated permutations by autonomous AI, adapting in real time to simulated enemy AI before a human commander ever issues a single physical order?
That is a wild thought.
Are we looking at a future where the analytical doing, the actual intellectual act of creating the solution, is entirely outsourced to the machine?
It really forces you to rethink our place in the architecture. I mean, if the AI is designing the mission threads and running the stochastic models, what exactly is our role?
That's the million-dollar question.
Perhaps it brings us right back to the very beginning, ensuring that before the simulation even starts, we have asked the machine to solve the correct problem. Because even an advanced AI can perfectly engineer a bridge over the wrong river.
That's a great point.
Something to think about.
I hope you enjoyed today's deep dive. Why not take a moment and join the discussion in the LinkedIn group Tackling Complex Problems. Take care.